In this last video of section 13.1, I want to go over sort of summarizing what we've talked about, as well as the algebraic properties now of this system that we've developed. So what have we done? We've defined vectors, we've defined addition on those vectors. We've seen that geometrically, we've also seen how to compute it algebraically or numerically. We've done the same with scalar multiplication. We've talked about unit vectors, all these things, so we can talk about all these operations in terms of position vectors and unit vectors. Talked about direction of vectors, things like this. But one last thing, so now that we have this, we have vectors, these new objects, together with two operations. So we have vectors, and we have two ways to operate on these. We have scalar multiplication, scalar multiples is one operation, and we also have vector addition, same as subtraction. They're really the same. As I've mentioned before, they're the same operation. So these two ways to operate on vectors, combine vectors with other things. And so we need to talk about what are the rules for these things? Where do these things come from? What things do we know hold true in general? Each of these things that I'm going to mention, each of these 10 rules that we have here, should be intuitive, and each can be proved, and especially if you have a good geometric picture in your head, maybe this first one will make sense. If I do u plus v, it's the same as doing v plus u. So that is vector addition commute. So why is this true? Like I said, each of these can be proved. Each of these can be intuited from the geometric picture. So u plus v, so that would be, here's u, let's say, and then I do, say, v like this. U plus v would be here. So what if I do v first, and then I do u? There would be u plus v. It's the same vector. So u plus v is the same as v plus u. This geometric definition of it commutes. If I add three vectors together, well, I have to pick which two I'm going to do first, which two I'm going to do second. I can't add three all at the same time. Well, actually, what this is saying is that I can. U plus v plus w, if I do it in that order, same as doing u, added that to, so this first one was commutative property. This one is the associative property. Again, this can be worked out geometrically in much the same way as up here. And what this means is that we don't, if we're just adding a bunch of vectors together, we really don't need parentheses. So each of these, as we'll see later on, I could just write this as u plus v plus w. That I don't have to specify which two I should combine first and add to the other one. It doesn't matter. That's what associativity tells me. It doesn't matter. I don't need to write parentheses if I'm just adding a bunch of vectors together. If I take any vector and add it to the zero vector, well, the zero vector, we'll think about this one numerically, is the position vector 0, 0. So with all of the numerical results for addition of vectors, I would add nothing to the x component of v, I'd add nothing to the y component of v, and so I really just get v back. So that is u acts as a identity element. So this is identity. The zero vector. V plus negative v, well, that gives me the zero vector. Again, so let's say I take v and I add that to negative v. So negative v would come back the same way. That's negative v. And if I put these two on top of each other, well, I end up back where I started. So I get, so I get the zero vector. I've already written that up here. So that's a nice property. It means I can cancel things off from two sides of an equation. So that is, if I have something like, let's say, well, you know, why is this useful? Why do I care? Well, let's say I know that u plus v vectors give me a third vector w, and I know, let's see, I've figured out v and w, and I want to figure out what u is. Well, I can subtract the vector v from both sides. And now I can use this property number 4 to say v minus v, that's 0. So this is u is equal to w minus v. So what we're really doing here is we're establishing an algebraic system for how these vectors work with these two operations, addition and scalar multiplication. What that allows me to do is solve equations involving vectors. So another thing here is if I take two vectors u and v, I add them together and then I scale that. Well, that's exactly the same as first scaling u, scaling v, and adding the two results together. Again, something else that is quite useful. All right, let's see if so that's adding two vectors and then scaling them. I can do this. So you can think of this like a distributive property. So I'll call this distributive property 1. Well, there's another distributive property, and that's if I add two scalars together and then use that to scale a vector v. That's actually the same as taking the first scalar, scaling v, and then adding that to the scaled version of v by c. And so this is also a distributive property, but because we have two operations, we have two distributive properties. A consequence of this is that 0, the scalar 0 times any vector v, and I've mentioned this before, gives me the 0 vector. Again, precision in notation. 0 scalar times any vector v gives me the 0 vector. This 0 and this 0 are totally different objects, but as you see, there's a good reason why we call it the 0 vector and the 0 scalar. If I scale the 0 vector, well, the 0 vector has no length. So if I scale that, the result will also have no length. There's only one vector that has no length, and that's the 0 vector. We have another identity property of vectors that if I scale any vector by 1, well, I just get back v. And lastly, we have another associative property. So this is associative, maybe I'll call this associative number 1. Another associative property, if I scale a vector by c, and then I scale the resulting vector by a, well, this is actually the same as multiplying the two scalars and then scaling the vector v. So this is another associative property. So, this might be a little bit daunting. This might be a little bit confusing because we have like doubled up some properties. So play around with this. Try for each of these, try and come up with a geometric picture for why it's true. Try and prove this. Each of these. You can do it for every single one of these. And again, I want you to have the intuitive idea of why these things are true, because then you don't have to memorize 10 rules. I hate the term rules. They're not rules just handed down by some person on high saying these are the rules for vectors. They're not. These are consequences of how we've defined these operations. If we've defined them in such a way, then what we get are all of these very nice properties that tell us how these things work with each other, and they allow us to now go to the realm of algebra on vectors. So that's what's going on here. We have algebra on vectors. And so we're going to work with equations of vectors. Using these rules, we can solve for other vectors in terms of other ones. Rewrite things, come up with different expressions for vectors that'll be useful in describing positions and velocities. All this great stuff is going to come from these algebraic rules. Okay, so that's it for this section. I will see you next time in the next video. I'll see you there.